Welcome to 10 Minute Climate, the podcast brought to you by Beaverbrook Energy. Join Max.
Hi, I'm Max.
And Tony.
Hi, I'm Tony.
Who between them have got over 70 years of experience in the energy industry, and they're here to share it with you. It's everything you need to know, delivered in just 10 minutes. So let's get started.
So the grid, let's hope our viewers are sitting comfortably, because this is a bit technical, and it's let's try and keep it at a high level, because to some extent when you think about the grid, you're thinking about lots of extension cables plugged into each other. But of course, it's a hell of a lot more than that. What it is this massive distributed machine across the country that's delivering exactly the power at the voltage and amperage that we need at the moment we need it, for this light, for these microphones, for whatever it is. And it's an unbelievably big machine. Probably all the grids together, the biggest machine that humanity's ever made, I guess. And it started with, it's all about magnets. It's all about big magnets.
Spinning magnets next to wires, fundamentally. So the idea is that you actually, the Faraday principle about rotating magnets in a copper cage is fundamentally what you do.
Yeah, I mean, what you're doing is you're moving the electrons around. But obviously, down the other end, you've got like your mobile phone, which needs exactly the right electrons at the right moment in the right way, and you've got to control those pretty carefully, and that's complicated.
Yeah, but that's just the same as any other system, and they're the electrical equivalents of valves and tanks, and it's just the same as plumbing. I mean, upstream from that bit, spinning your magnets can take a lot of forms. You can make a wheel go round with water, which is basically what hydropower is. You can make a wheel go round with steam, which is a steam turbine, which is what nuclear power stations are actually.
Where you're heating the water through various things.
The only difference in most power stations is how you heat the fluid up, the steam or the gas or whatever, that makes the big magnets go round and round. Decomposition of nuclear material generates heat, which makes steam. Burning coal, burning gas, burning oil all generate steam, which makes the big fan go round and round.
And this is where people got very worried about 20, 30 years ago. They said, oh, well, we're going to need the big magnets spinning to keep the grid going.
Yep.
But if you're going to build solar or wind, that's not going to work. I mean, wind is big magnets or smaller magnets going around, but because of the nature of it, it's got stuff in between that means it doesn't deliver power in the same way. So it's a totally different system with the energy transition. Yeah,
because if you go to a conventional power station, you have the alternator bit at one end, which is a big lump of metal, don't get me wrong, with the magnets on it, which goes round and round and round. But attached to that is a huge, great lump of metal, which is the turbine, which is turned around by steam or gas or whatever.
It's a jet engine.
It's massive. Massive weight. I mean, hundreds of tons of steel rotating at very high speed, thousands of revolutions per minute. And you can't replicate that with a wind turbine, because the bit in the nacelle of a wind turbine is actually quite small mechanically compared to the blades turning round, which gives you the rotation. And as you say, what you used to get was a flywheel effect from these big lumps of metal, which meant that as you got changes in the grid, in the amount of energy that's being taken or delivered, the flywheel effect of all these big lumps of metal going round and round used to be steadying. If you take those away, the grid becomes more volatile in terms of controlling the voltage and the frequency.
So something happens somewhere. These big wheels kind of just slow it all down. They calm everybody down. All right, boys, just calm down. Let's not do anything stupid.
Well, it's like when you hit a hill with your car. If you don't put the accelerator down a little bit more, you'll slow down.
Well, so what you're saying is you've got a grid and one power station trips and the other one's just keeping everything going.
Yeah. And then when you've got the flywheel effect of these big lumps of metal, they can tend to carry you forward with this mechanical energy over that bump. But if you haven't got that inertia control in the grid, everything goes a bit and slows down.
And electrical things don't like that.
Yeah, because obviously the frequency and the voltage are really quite critical for the operation of so many machines and lighting and everything else. And if they go out of a very small controlled band, they switch off for safety purposes. So you get almost a domino effect, a cascade effect, that something switches off, which makes something else switch off.
2003, it happened in North America, didn't it? And they lost, 50 million people? got off the grid, there was a cascading series of blackouts from one fault,
Yeah.
and it just went boom, 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 boom.
We had a similar thing here couple of years ago. We lost a lot of the West Midlands, I think it was, because the interconnector with France, because there's a big cable connects us to France that has about 2 gigawatts connection on, which is about 3 big power stations, and it tripped. So all of a sudden, this load was thrown onto the existing power stations in the UK, and they all went, "Ooh," and the voltage and frequency dropped sufficiently in a certain area of the UK that everything went ding, 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 ding.
And he couldn't react fast enough. And
No.
what we've got now is batteries, which obviously
Yes.
are really fast.
Instantaneous. I mean,
Well, not instantaneous. There's a time,
milliseconds.
but yeah,
milliseconds. Quicker than you can speed up a turbine, quicker than you can put more coal on the fire.
Quicker than you can dump water down a mountain.
Exactly.
Batteries are bang on, and that's what's balancing the grid. And the fact that we're now interconnected to other countries as well.
Yeah.
So those things can go.
Spreading the load, really, is what
Yeah.
we're doing. What we're doing is not just relying on the resilience of our grid now, but we're connected to Ireland, Belgium, Norway, France.
There have been some instances where grids have run with no fossil fuel at all. Not for that long, but certainly for a couple of weeks. I think Portugal did last year. Various different other grids or sections of the grid. I think one in Australia. They'll run for certain periods of time without any fossils at all. So it's being shown that it can be done because people were skeptical. In the 1990s, people said, no, you're always going to have coal and gas.
34%, I think, we used to be quoted that you had to have 34% of hydrocarbons, big spinning bits of metal, otherwise nothing would ever operate. In reality, don't need it. And in fact, the Australians are investing massively in grid-scale batteries because they've got so much solar opportunity. They're actually building gigawatt-scale batteries, so bigger than a power station. As more batteries become available, obviously this counterweight idea is going to be more steadying for the grid. Another strange term that comes into use when you're talking about the grid is ducks, the duck curve.
Yeah. The duck curve, so it's basically solar. Sun comes up every day, pretty reliable, depends on some clouds,
Mostly.
but essentially you know when the solar panels are going to be generating, and what happens is the duck curve actually refers to the price of power that drops down like a duck's back and then comes back up in the evening. It's predictable, but you know when solar is going to come on. But what do you do in the morning and the evening when you don't have solar? And the answer is in the morning, not very much because it's dark and it's been a long time since the sun. But the evening, you can shift batteries there. And that's happening enormously in California. They've got a huge build out of batteries. And it's materially changing the profile of when solar comes on the system and pricing as well.
So if you've got this duck curve, which is being changed, a changing duck
Sliced?
curve. Yeah,
You're
it could
slicing
be.
the duck?
Yeah, that's going to mean that the pricing of power is going to be on a timescale, which doesn't necessarily currently relate to the way we use energy.
Well, you've got currently a massive problem because you're generating all your solar during the day.
Yeah.
So the price goes to zero because you've got, in many cases, too much.
Yeah.
And particularly in Spain, they're generating way too much. They have to shut it down. You're getting, literally a few euros a megawatt hour when you should be getting 30 or 40 or something.
Mm-hmm.
So yeah, shifting to the evening is what's going to happen. I don't think it's going to change the working day necessarily, but it's gonna move power from the middle to the end to the evening, which enables the solar farms to make more money, which means they're economic. Currently, if you built a solar farm in Spain, you don't make any money because you're selling it in the day for a few euros. So no one's building it. So you've got to build it with batteries. So you're getting the evening pricing, which is always higher because there's greater demand for electricity generally, and there's no solar. So you need to move it.
But would it make sense if you've got a high energy intensity process? You start doing it at 4 o'clock in the morning when the sun comes up in California, or 6 o'clock in the morning, whenever it is, and then you stop doing it at 6 o'clock at night. Whereas at the moment, the working day tends to start between sort of 8 and 9 and finishes between sort of 5 and 7.
Oh, it does. But industrial processes, there's tend to run as much as possible. If you're going to build a factory, you want to use it as much as possible. But I think it's an interesting question because in certain places, you're going to be getting very, very low electricity prices. In sunny places where when you've got long days, you're going to get very cheap prices at certain times? And will it make sense to build factories to use them only some of the time when energy is very cheap?
At some point, it's going to be in the cost benefit curve, it's going to be worth building 2 factories or double the size factory, which you only run for half the time because of the energy cost.
A lot of people saying that.
Yeah.
Yet to be convinced.
Thanks so much for tuning in to today's episode. If you enjoyed the conversation, don't forget to like, subscribe, and leave us a review. It really helps us grow and continue bringing you valuable content. If you're curious to learn more about Beaverbrook Energy and how we're navigating the future of energy, feel free to reach out to us directly. And for those looking for quick, actionable insights on the energy transition, be sure to subscribe to our 10-second climate newsletter, delivered every weekend with essential intelligence to help business leaders stay ahead of the curve. We appreciate you listening, and we look forward to having you join us again next time. Stay informed, stay engaged, and take care.